All right. So when we are studying the uniform series analysis, we have studied the relationships between a uniform series of cash flows and the future value. Uniform series compound amount factor helps us to calculate the total accumulated future value in a savings account if you have a uniform series of cash flows into that account. And the uniform series sinking fund factor is doing the opposite. It helps us to calculate the necessary installment size to be invested in the end of each year to get a total accumulated amount of F. So this time we are going to study relationships between a uniform series of cash flows and the present value. And here we start with the uniform series capital recovery factor. Now, suppose that a given sum of money P is deposited in a savings account. So right now, at time zero, you have deposited a money P in that account, and that money, as long as it stays in the savings account, it is going to earn interest at rate I per year that compounds annually. Now, what you are going to do is, after investing that amount, you are going to withdraw a fixed amount of A in the end of each year. And you are going to do this for n years. Okay, n years. So the question here is this. What should be the value of this installment size A? B, so that in the end of the nth year, the total amount will be depleted. Okay, so we are just going to finish or exhaust the total invested amount in the savings account in n years, and what is the maximum value that I can draw in the end of every year A. Okay, so that is basically in the end of year each year. So what is this value of A? So another perspective to explain this problem is this. Suppose that you have gone to a credit company or a bank and you have taken a loan of P. So we are drawing this cash flow diagram from the bank's perspective. So the bank has given you a loan of size P, and you are basically going to pay your loan or pay your debts in n years. So in n, there is a installment plan, there is a payment plan which consists of n installments in the end of each year, and the bank is going to make you pay an installment of size A in the end of each year. So the question here is this. If the bank is exposing you to an interest rate I that compounds annually, in that case, what should be your payment sizes so that you can complete your debt, okay, close your debt in the end of the NT. So basically, if you go to a bank and ask for credit or money, this is the situation that you are going to see. If you go and ask for a loan of $100,000 to be repaid in, let's just say, 10 years, then they are going to use the calculations which we are going to learn in a moment later to calculate the annual payment size that you need to pay in the end of each year. So let's try to solve this problem. So how can we relate the uniform series and the present world? Okay. Now, what we are going to do is we will use our previous knowledge from the previous parts of this course. So we have studied the single payment analysis. We have studied half of the uniform series analysis. So we know the compound amount factor now. Now, we are going to relate the present value to the annual payment sizes. Okay, so in this cash flow diagram, what I can do is I can calculate the future equivalent of this present value, right? So I will use the time value of the money and I will determine the equivalent future value in the end of the nth year for our principal in the beginning of these years. So what I'm going to do is I will convert this P principal to the equivalent future value by multiplying it with single payment compound amount factor, F over P under I% interest rate for n years. So P times F over P becomes F. Now, since we have determined the future value equivalent of this principal value, how I can convert this future value to the annual payments is what? I'm just going to use the sinking fund factor, right? So if I multiply F with the uniform series sinking fund factor A over F, I will be calculating the annual installment size of this uniform series. So basically, in the extended notation, if I want to define A for a given present value, or if I take a loan from the bank of size P and I want to determine the annual payment size that I need to pay, I'm going to multiply my principal size with the uniform series capital recovery factor A over P under I% interest rate for n years. And that A, instead of multiplying it with A over P, what I can do is first I multiply my principal with the single payment compound amount factor, then the value will be actually the future value of that principal. And if you multiply that future value with the uniform series sinking fund factor, you are going to get the annually equivalent value. Okay, so P times F over P times A over F. In this formulation, if you are careful, you will see that F's here will cancel out, and what you are going to get is A over P. Basically, the factor which converts the initial principal to the uniform series annual investment or installment sizes, which is called the uniform series capital recovery factor, is the product of the single payment compound amount factor and the uniform series sinking fund factor. So basically, we are using a two-step approach here. I multiply P with F over P, then A over F. So it will basically be multiplied with A over P. And in the actual formula, F over P is 1 plus I to the power n, and the sinking fund factor is I over 1 plus I to the power n minus 1. So when you multiply these formulations, you will get the formula for the uniform series capital recovery factor, which converts our principal to the annual payment size. I times 1 plus I to the power n divided by 1 plus I over n minus 1. Now, the uniform series capital recovery factor, A over P, is formulated in the previous page as here. So A over P is equal to I times 1 plus I to the power n divided by 1 plus I to the power n minus 1. And the extended notation that we are going to use for the uniform series capital recovery factor is A over P under I% interest rate for n years. And there is a separate column in our compound interest tables where we can search for the values of capital recovery factor. Now we are going to solve a question related to that to understand it better. An engineer who is about to retire has accumulated $50,000 in a savings account that pays interest at a rate of 6% per year compounded annually. So right now, at the current time point, the engineer has $50,000 in that savings account, and that savings account is accumulating the money, compounding the money at a 6% interest rate per year, and it compounds. Okay, it compounds on annual basis. Now, the engineer wishes to withdraw a fixed sum of money at the end of each year for 10 years. So for 10 years, the engineer is going to withdraw an equal amount of money. Okay. Now the question here is this: what is the maximum amount that can be withdrawn so that all of the money in that account will be depleted? Okay. So because it says what is the maximum amount he or she can withdraw, so we are just going to assume that the money is going to completely deplete or exhaust in the end of the 10 years. Okay. So basically, if we go back to this cash flow diagram, the question gives us that P is equal to $50,000, the current amount in the account right now. And for n years, for n equal to 10, for 10 years, the engineer is going to withdraw equal sized payments. And how we are going to calculate value? By using the uniform series capital recovery factor. So principal is $50,000. The annually compounding interest rate as decimal is 0.06, and the number of investment years is 10. Either we can use the formula to calculate the annual installment size by multiplying the principal with the uniform series capital recovery factor, plugging in values of P, the interest rate per year as decimal, and the number of investment years, 10. You will get $6,793.40. So here's the thing. If you have $50,000 right now in that savings account that pays 6% interest rate per year compounding annually, in that case, in each year for 10 years, in the end of each year, you can withdraw $6,793.40. So for 10 years, the total amount that is withdrawn would be $67,930 approximately. Okay, so more than $50,000, but that's the thing basically. Okay, and this is basically a retirement account. I mean, for years and years, people accumulate money in their retirement funds. Okay, and after that, after they retire, they are basically taking money from their retirement account as salary. Okay, and this is how the retirement works. Okay. Now, you can also make the same calculations using the compound interest table. So you can say that my annual installment size A is equal to the principal times A over P under I% interest rate for n years. Okay. So A over P under I% interest rate for n years in parentheses is representing the uniform series capital recovery factor. And you multiply your principal with A over P under 6% for this question. So your I is 6%, and the number of investment years is 10. And what we are going to do is we are going to search for this value from our table. If you go back to our compound interest factors table, we are at page of 6%. And the third column corresponds to uniform series capital recovery factor. And how many years of investments do we have in this question? 10. So your uniform series capital recovery factor is 0.13587. So we are exactly going to use that value in our formulation, and we are going to get a value which is a little different, only a little different than the value that we have found through the direct formulation. Now, one point here, my friends, you need to be careful about. So you see in this table, compound interest factors, all of the compound factors are written with 4 decimal digits after the decimal point. Okay. However, only the capital recovery factor has 5 decimal points after the decimal digit. So when you are making calculations using the formulation, please, if you are going to round the factor that you have calculated, use 5 decimal digits, especially for the uniform series capital recovery factor. Now, let me explain the story of the previous question here. So the engineer has $50,000 in his or her savings account. As you can see here, we have $50,000 here. And in the end of the year, the money is going to be compounded in an amount with 6% interest rate. So $50,000 will become $53,000 with 6% interest rate per year. In the end of the first year, the engineer is going to withdraw $6,793. And the remaining amount in the end of the first year will again be compounded with 6% interest rate to a value. And in the end of the second year, another installment will be withdrawn by the engineer. So every year, the procedure is going to go like that. However, as the money depletes, as the money gets to a lower amount in the following years, the interest that it is going to gain is also going to get reduced, right? So because the interest amounts are dependent on the amount of money that is kept in the savings account. As you can see, the slope of these dashed lines are decreasing in each following year. In fact, in the last year, the engineer has only a small amount of money in the account, which gains interest for 1 year, and after gaining the interest, that money will exactly be equal to $6,793.4, and when it is withdrawn, the whole money will be it. So this is basically how we solve questions using the uniform series capital recovery factor. So the next part is going to be studied in the next video.